Good morning guys. Today we will see another example which is based on your truss structure, or we will solve this example by using our finite elemental procedure. Okay, in previous 2 to 3 lectures we have solved some examples related to our truss problem. Okay, now in this example we will solve this truss problem by using our finite elemental procedure. Okay, so I will read the example. Okay, so for a 2-bar truss problem, or for a 2-bar truss structure shown in figure, determine the displacement in y direction at node 1. Okay, displacement in y direction at node 1. Okay, so already this diagram is given. Okay, and in this diagram this node is considered to be a node 1. So find out the displacement in y direction at node 1. Okay, then and axial force in each element. Also find out the axial forces in each element. So the problem is what? First find out the displacement in y direction for node 1. Then find out the forces in each element. It means find out the displacements in each displacement at each node. Horizontal displacement as well as vertical displacement. Then next is what? Find out the forces in each member, axial forces in each member. A force of 1000 kN is applied at node 1. Okay, a force of 1000 kN is applied at node 2. Sorry, at node 2. Okay, this is node 2. This is node 1. Sorry. Actually, determine the displacement in y direction at node 2. Actually, at this point we need to find out the displacement. Similarly, a force of 1000 kN is acting at node 2 in a negative applied at node 1 in a negative x direction. Okay, so force P is equal to 1000 kN. It is acting at node 2 in negative x direction. While node 2 settles an amount of delta is equal to 50 mm. Settles an amount of delta is equal to 50 mm in negative y direction. Okay, so delta is equal to 50 mm. This node settles an amount of delta is equal to 50 mm in negative y direction. So this displacement delta is equal to 50 mm is given. And let E is equal to 210 gigapascal and area is equal to 600 mm square for each element. Then find out the displacement in y direction at node 2, or find out the displacements in each or at each node. Also as well find out the reactions at the supports. Also find out the next problem. What will be the next problem? Find out the stresses in each member. Okay, so this is the example. All the data it is given. I have written all the data, given data on the blackboard. Okay, so there are 3 nodes, 2 elements. This is first element, this is second element, and 3 nodes. This is first node, this is second node, and this is third node. Also the length of this second element is given. It is equal to 4000 mm, and the distance between node 1 and node 3 is given equal to 3000 mm. So first we need to find, or we need to construct a table which includes the element, then length, then theta, then L is equal to cos theta value, M is equal to sin theta value, then L square, why L square is required? Because we need to construct our elemental stiffness matrix. L square is required, M square, and finally L. Okay, as there are 2 elements, element 1 and element 2, so we need to construct this table for 2 elements. Okay, so for first element, what is the length? This is first element. So what will be the length? So L1 is is nothing but square root of, by using the Pythagoras theorem, L1 is nothing but square root of this square plus this side square. So 3000 square plus 4000 square. So L1 it will become equal to 5000. So L1 will become equal to 5000. L2 for element 2, L2 is equal to 4000 mm. L2 is equal to 4000 mm. Now theta. What is the theta 1 and what is theta 2? So select. So here node 3 is selected as our reference node. So this is your x direction and this is your y direction. Okay, so node 1, node 3 is selected as a reference node. So at this node, this is your global coordinate system xy. So this element 1, what is the value of theta? Theta is nothing but theta. It is the angle of that element with x-axis. Okay, so this element is parallel to this x-axis, so angle will be equal to 0. Now theta 2, so this is your x-axis, so theta 2 will become equal to this. This is your theta. So theta 2 will become, actually this is your right angle triangle. Okay, so theta 2 will become 90, this 90 plus this small angle. Suppose this small angle is alpha. So 90 plus alpha. Now this alpha is nothing but this is your right angle triangle. So alpha will become tan inverse of front side by adjacent side. So front side it is equal to 4000. So tan inverse of 4000 divided by adjacent side. Adjacent side is equal to 3000. It is equal to 3000. So alpha will become equal to tan inverse of 4 by 3. So tan inverse of 4 by 3. So alpha will become equal to 53.30. 53.30. So theta 2 will become equal to this plus this 90 plus 53.30. So it will become equal to 143.3. 143.3 degrees. Okay, so theta 2 is equal to 143.1. Okay, so finally theta values we have determined. Now next is what? L. Now L is nothing but cos theta. So L cos 0 is equal to 1. Sin 0 is equal to 0. Now L square means 1 square 1, n square 0, Ln 0 into 1 0. Okay. Similarly, L is equal to cos theta. Cos 143.30. Now cos 143.30 is equal to minus 0.8. Minus 0.8. Now sin 143.3 it is equal to 0.6. Okay, now L square will become minus 0.8 square is 0.64. L square 0.6 square is 0.36 and ln 0.6 into minus 0.8. So it will become minus 0.48. So in this way you will get your final table. By using this table now we will construct our 11th stiffness matrix. So first step is what? Now, so we have constructed this table, means which include length, theta, L, M, L square, M square and L. Why it is necessary? Because while constructing our elemental stiffness matrix, we need L square, Lm, M square values. Okay. So we know that the elemental stiffness matrix is I will write down this elemental stiffness matrix here. Okay. I will write down this elemental stiffness matrix for element 1 and element 3. So our standard elemental stiffness matrix is what? K is equal to AP by L in bracket L square LM minus L square minus LM. Then here M square, here then again L square, here then again M square. LM minus LM and minus L square minus M square. So LM minus LM minus L square minus M square minus LM. Okay, so you need to remember only this matrix. You need to remember only this matrix. By using this matrix, you can write the remaining term. Why? Because this is symmetric matrix. Okay. So this is your standard elementary stiffness matrix. Now for element 1, so for element 1, K1 is equal to A1 E1 by L1 into this matrix. Now L square for first element, L square is equal to 1. LM is equal to 0. Minus L square is equal to minus 1. Minus LM 0. Then LM 0, M square 0. LM 0, M square 0. So it will become 0, 0, 0, 0. Now minus L square is minus 1. LM 0. L square is 1, 0. Here also all terms 0. Okay. Now A into E by L. So by simplifying, area is given 600 into E. It is given 210 gigapascal. But we need to convert this value into Newton per mm square. Why? Because all the remaining terms are given in mm. Area is given in mm square, length is also given in mm. Also, we will convert this value in kilonewton per mm square because the parameter, actually this force value P, it is given in kilonewtons. So we will convert this value in kilonewton per mm square. So finally we will get all the reactions or forces in kilonewtons as well as the stresses in kilonewton per mm square. So convert this into kilonewton per mm square. So it will become 210 into 10 raised to power 3 megapascal. Now 1 megapascal is nothing but 1 Newton per mm square. So it will become 210 kilonewton per mm square. 210 kilonewton per mm square. So here we will write only 210. Well, 600 into 210 divided by length L1 is given 5000. So this will become 21 into 6 divided by 5. So 5 1.2. 12 into 1 2 1 25.2. This is the final value. So instead of this, this value is 25.2. So instead of 1, we will write down 25. So 25.2. Here also minus 25 point. Minus 25 point, and this will become 25 point. So K1 will become equal to this value. Next is what? K2. K2 value will become K2 is equal to A2 into E2 divided by L in bracket. So here K1 value, I will write down this K1 here. So K1 is equal to 25.20 minus 25.20 0 0 0 0 minus 25.2, 0, 25.2, 0, 0, 0, 0, 0. Okay, so this is your first element distribution matrix. Now we will find out second, K2. K2 is nothing but A2 E2 by L2 in bracket this matrix. Now L square is what? For second element. Now first element it is over. So we will do this. So for second element L square is what? 0.64. Ln is what? Minus 0.48. Minus L square means minus 0.64. Minus Ln means minus minus plus. This will become 0.48. We will write only this upper diagonal matrix. So M square is what? 0.36. Minus Ln means what? Minus Ln means minus minus plus 0.48. Minus L square means minus 0.36. Then here L square is 0.64. M square is 0.36. And here Ln means minus 0.40. Ln means minus 0.40. So now you can write the remaining terms as this is symmetric. So we will write this row minus 0.48, 0.48 minus 0.48. Then this row minus 0.64 minus 0.36 and finally 0.40. Okay, so this is your second elementary stiffness matrix. Now we need to simplify this A2 divided by L2. So A raised 600 into E is also same 210 divided by length L2 is equal to 4000. So this will become 1.5 into 21, 31.5. Okay, so this value will become equal to 31.5. So 31.5. So instead of this will become 31.5 this matrix. Okay. So now we need to multiply this 31.5 into this whole matrix. So by on multiplication we will get a new elementary stiffness matrix for this second element. So here I will write this matrix. So K2 is written as, okay, after multiplication you will get this matrix. So this will become equal to 20.16 minus 15.12 minus 20.6 15.12 minus 15.12 11.34 15.12 minus 11.34 minus 20.6 15.12 20.16 minus 15.12 15.12 minus 11.34 minus 15.12 11.32. Okay, so in this way you will get this second elemental stiffness matrix. Now next step is what? Now we will construct our global stiffness matrix for these two elements, as there are two elements. This is one and this is. Okay, so we know that this is the elemental stiffness matrix. Now from this elemental stiffness matrix we need to construct our global stiffness matrix. So this is your example. node 2 and node. So at node 1 there will be displacement u1 and this is v1. At node 2 u2 v2 and at node 3 u3 and v2. Okay, so the connectivity of first element is in between node u1 and u1 v1, u2 v2. So connectivity of node is this first element connectivity is between node 1 and node. It means between u1 v1, u2 v2. So first node is written in u1 v1, u2 v2, u1 v1, u2 v2. Second element, the connectivity of second element is in between node 2 and node 3, means u2 v2, u3 v3. So this is your u2 v2, u3 v3, u2 v2, u3 and v3. So now by using these two elemental stiffness matrices, we will construct our global stiffness matrix. So global stiffness matrix, order of this global stiffness matrix, what will be the order of this global stiffness matrix? As we know that there are 3 nodes and 2 degrees of freedom at each node. So this order will become equal to 6. So 6 by 6 matrix would be there. So this is your u1. So 6 by 6 matrix should be there. Okay. So K will become equal to u1 v1 u2 v2 u3 and v2. Similarly u1 v1 u2 v2 u3 and v2. In this way we need to construct this 6 by 6 matrix. So first element, the connectivity of first element is in between node 1 and 2. So connectivity is in between u1 v1, u2 v2. So u1 v1. So this is the connectivity of first matrix. The connectivity of second matrix, this is between u2 v2 and u3 v3 rows and columns. So u2 v2, from this it will start from this and end at this. Okay, so this is the connectivity. So we will write down these elemental stiffness matrices or the global stiffness matrix. So we will get 25.2, 0, minus 25.2, 0, 0, 0, 0, 0, then minus 25.2, 0, 25.2, 0, 0, 0, 0 and 0. Okay, so this is the connectivity of this is the first elemental stiffness matrix. Now second elemental stiffness matrix, we need to write down this in between node 2 and 3, means between rows and columns, u2 v2 u3 v3. So this will start from u2, from this point it will start. So 20.6 plus 20.16 minus 15.12 minus 20.16 and minus 15.12. Okay, next row minus 15.12 here plus minus 15.12, then 11.34 plus 11.34, then 15.12. Then next minus 11.30. Now u3, from this it will start from this row this column. Okay, so minus 20.60 minus 20.60, 15.12. Then next 20.60. And final minus 15.12. Now final row is minus 15.12. Then minus 11.34. Then minus 15.12. And finally 11.34. So in this way the remaining terms are 0. Okay, so in this way you can write your global stiffness matrix. Okay, so we will just simplify these terms. So 25.20 plus 20.60, so 45.36. So this will become 45.36. This will become minus 15.12. Minus 15.12. This will also minus 15.12. Minus 11.34. So in this way you will get the final global stiffness matrix. Okay. Now we need to write down this global stiffness matrix in our relationship. Which relationship? Force is equal to global stiffness matrix into your displacement. So we will write down this as this is your global stiffness matrix, and the forces are F1x, F1y, F2x, F2y. Means force in x direction, force at node 1 in x direction, force at node 1 in y direction, force at node 2 in x direction, force at node 2 in y direction. Similarly, force at node 3 in x direction, force at node 3 in y direction. Okay. So in this way we have written our displacement relations. Similarly, displacements can be written as this is your U1, V1, U2, V2, U3, and finally V. Okay, so in this way you can write this relationship. Now we need to apply. Now next step is what? Apply the boundary conditions. So we know that this is the problem. This is the problem. This is your first node. This is your second node. And this is your third node. At second node, roller support is given. Okay. So also the distance of 50 mm. This delta is given equal to 50 mm. So at first node, this is your U1, this is your V1. Similarly, F1x, F1. At node 2, this force is given equal to 1000 actually. P is equal to 1000 is given. So at node 2, this is your F2x and this is your F2y. F1x, F1y, F2x, F2y, F3x and F3. So at node 1, this P is given equal to 1000 kilo Newton. Similarly, this displacement delta is given equal to 50 mm. So at node 2, this is your U2 and this is your V2. Similarly, F2x in horizontal, F2y in vertical. And at node 3, this is your U3 also, F3y, and this is your V3 also. Sorry, F3x and F3y. Okay. So now we will apply our boundary conditions. So boundary conditions, first we will apply the boundary conditions for displacement. So these are the displacements U1, V1, U2, V2, U3, V3. So here from this diagram we will apply the displacement. So at node 1, this node 1 it is fixed one. So both U1 and V1 will become equal to 0 because of this fixed support. It will become 0. So U1 equal to 0, V1 equal to 0. Similarly, U3 and V2, this node is also fixed. Okay, this node is fixed, so that this U3 and V3 will become also equal to 0. So U1, V1, 0, U1, 0, V1, 0. Similarly, U3, 0, V3, 0. Now next is at node 2. Now add this node, this vertical displacement in a negative y direction is given at this node 2. It means the value of V2 is given. Okay. If it is not given, then we will assume it equal to 0 because of this vertical support. But this node is displaced initially by 50 mm, so that we need to take this 50 mm into account. So this V2. Now this displacement is in y direction. Now y direction displacement is what? Or V2. But this displacement it is in negative direction. So we need to take it as a negative. So V2 will become minus 50 mm. Okay. So V2 will become minus 50 mm. Now U2. So U2, we need to find out this U2. Why? Because due to this roller support, there must be a movement of this node 2 in a horizontal direction. It should be in positive or it should be in negative direction. But there must be some displacement at node 2 in horizontal direction. So we need to find out this U2 value. So U2 will become unknown. Okay, so from this V2 is equal to minus 50. So V2 it is equal to minus 50. Why minus 50? Because this is taken in a negative direction, and we need to find out U2 value. Okay. Now next is what? For forces. Now this F1x, F1y, F1x, F1y, these are the reactions, support reactions. It is nothing but equal to R1x, R1y. Now F2x, F2x. Now this is the force acting at node 2 in a horizontal direction. It means this F2x it is given equal to minus 1000 Newton. Minus, why minus? Because in a positive direction, in this direction we will take it as a take this value as a positive, but this is given in a negative direction, so we need to take it as a negative. So minus 1000 kN is equal to F2x. So F2x is equal to minus 1000 kN. So F2x will become minus 1000. Okay. Now F2y is nothing but this support reaction due to this roller support. So F2y will become equal to R2y. F3x and F3y, these are the support reactions. R3x and R3. So in this way we have applied our boundary conditions. Now next step is what? Elimination approach. Okay, so by using this elimination approach, we know that which displacement values are 0 on RHS side. Eliminate these rows and columns. Finally, you will get the remaining equations, 2 or 3 remaining equations. By using these 2 or 3 remaining equations, you can get the displacement value. So these displacements are 0, u1, v1, u3, v3. So eliminate u1 row, u1 column, v1 row, v1 column, then u3 row, u3 column, and v3 row, v3 column. Okay, so remaining terms are, these are the remaining terms. So these are the two equations. So we will write down minus 1000 is equal to 45.36 times u2 minus 15.12 times v2. v2 is nothing but 45.36 into u2. Sorry, we will write down the matrix form first. So this will become minus 1000. This will become R2. It is equal to 45.36 minus 15.12 minus 15.12 11.30 is equal to these displacements u2 and v2 is equal to minus 50. So this is your u2 and this is your minus 50. So from first equation itself we will get the value minus 1000 is equal to 45.36 times u2 plus minus 15.12 into minus 50. So by solving this equation you will get u2 as, so value of u2 is equal to minus 38.71 minus 38.71. Okay, so by solving this you will get this, displacement value minus 38.71. Okay, now we need to find out r1x, r1y, r2y, r3x and r3y. Just we need to cross check whether this displacement value is correct or not. So r1x value, it is given, or we can determine this r1x value from this first equation. It means 25.2 0, this 0 minus 25.2 into u2 value minus 25.2 minus 25.2 into u, and u2 is nothing but this. So from this you will get r1x as 975.8. It means 976 kilo. Okay, this is your r1x. Now r1y. So r1y, as this row contains all the values are 0. So r1y is equal to 0. So r1y value, r1y is equal to 0. Next, f2x is known. r2y is equal to r2y. So to find out 0 into this 0, 0 into this 0, minus 15.12 into u2 plus 11.34 into v2, and all these remaining terms are 0. So minus 15.12 minus 15.12 into U2. U2 is what? Minus 38.71 plus R4 minus 15.12 into U plus 11.34 into minus 50. 11.34 into minus 50. So by solving this, you will get R2y as, so you will get R2y equal to 18.30. 18.30 kilonewton. Now next is R3x. We need to find out this R3x. R3x is nothing but 0 into this 0, 0 into this 0. 20.16 into U2. 20.16 into U2 plus 20.16 into U2 plus 15.12 into minus 15.12 into minus. So from this you will get R3x. R3x as, by putting the U2 you will get R3x as 24 kilonewton. Okay, and finally R3y. So R3y is nothing but 0, 0, 0, 0. 15.12 into U2 plus minus 11.34 into minus 50. So 15.12 into U2 plus minus 11.34 into this V2 minus 50. Minus 50. So from this you will get R3y by taking the value of U2. R3y as 18.30. R3y as R3y is equal to minus 18.30. Minus 18.30. Okay, so finally you will get all the values. U2 is equal to minus 38.71 mm. Then R1x is equal to 976 kilonewton. R1y is equal to 0. R2y is equal to 80.30 kilonewton. R3s is equal to 24.24 kilonewton. So we need to just cross-fire. So as we know that this U2 is equal to 38.74. So as we know that this is the example. Okay, and at this node, 1000 kilonewton force is active. This is your R3y. This is your R3x. Similarly, this is your R2x, and this is your R2y, and this is your R1x, R1. Okay, so by putting all the values, R3x is equal to 24, R3y is equal to minus 18.3, R2x is equal to R2x. Actually, R2x there is not R2x. Only this R2x is nothing but minus 1000. It is nothing but this force minus 1000. Okay. Or you can write this is nothing but your R2x. Then R2y is equal to 18.30. And this is your minus 18.30. R1x is equal to R1x 976. Okay. So from this we will conclude that this 1000 kilonewton force, this is acting in a negative direction, and it is balanced by this R3x in positive direction 24 plus this R1x in positive direction. So 976 plus 24, it is equal to 1000, which this force is balanced, this force is acting, these two forces are acting in this positive direction and its magnitude is equal to 1000 and it is balanced by this 1000 kilonewton force which is acting in negative direction. Okay, so horizontal summation of Fx, it is balanced. Okay, now summation of Fy, we need to balance this Fy forces also, means vertical forces also. So at this node, this is minus 18.3, it means it is acting downward, 18.3. Okay, and at this force, this is minus 18.3 and this is plus 18.3. So it is acting in vertical direction, vertical positive direction. So this, and at this R1y is equal to 0. So this 18.30 is balanced by this minus 18.30. It means our displacement value U2 is equal to minus 38.71 is correct. Okay, so these are the answers for your support reactions or forces, and also we have determined our displacement value U2 at this node 2. Okay, because at this node 2 we have determined our displacement value U2 and V2. Okay, so this is this example, this is some changes were there in this example, because this support, roller support is given, also this support is displaced by 50 mm in a vertically downward direction. So some changes are there were some changes in this example. So we have solved such type of examples also, and such type of examples will ask in your examination for 10 to 12 marks. Okay, because there are only 2 elements, so it will be asked in your examination for 10 to 12 marks. So here we will conclude our lecture. I will conclude this lecture, and from next lecture we will start our next topic. Okay, so thank you.